Hello, everyone. Welcome. So today we will do one last final review for the final exam here. Okay. So let's get started. So let's first talk about nomenclature. So nomenclature, you can expect at least maybe a couple nomenclature questions because nomenclature is an important part of organic, and so it might be best that we think about nomenclature a little bit. Don't completely put it out of our minds. All right, so let's remember, and a big part of nomenclature is now naming alcohols. So we're going to do that, okay? So we have, remember to name alcohols, we name the chain we number the chain that contains the oxygen atom in the parent chain. So the lowest number for the alcohol will get priority. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So this will be so the parent name is going to be dodecane. And the alcohol is at the 3 position. Okay, so there's two names we can. There's two ways we can name the parent chain. We could do dodecanol. We take dodecane, drop the e, and add all. Or we can also do this dodecan dash 3 dash all to indicate that the alcohol is in the 3rd position. Okay. All right, so we have a few substituents here. We have 410 diethyl. And at the 7th position, we have 1 methylpropyl right? So if we kind of number this in a different color here, 1, 2, 3. So that gives us 1 methylpropyl, 1 methylpropyl as our substituent there. Okay, so now let's name it. Okay, let's see. We can also name this 7-seek-butyl. But just remember that if you do name it seek-butyl, the seek doesn't count in alphabetization. But I'm guessing we can include it, but I don't think it matters too much. Okay. Yeah, it's best to just maybe just keep it one methylpropyl. It might make more sense that way. All right, so the full name is 4-10 diethyl 7 1 methyl propyl dodecan 3 all. Okay, so you can put 3 dodecanol. You could put 7-seek butyl. It's okay. So any of those substitutions will work. Okay. All right. So let's go on to the next one. All right. So here we have an ether. Okay. So in this case, when we have a ether here, ethers are substituents. So they don't really get priority like alcohols do. Okay. So first we can call this either the stereochemistry, or you could say cis, or you could say, if we were to assign the stereochemistry here, bromo would get the 1 position, right? Because it's first in priority alphabetically. And then in the 3 position, we would put the ether here. So we have first in the 1 position a bromo. And then in the 3rd position, you can say 3-1 methyl adoxy. So you have 1, 2 here, and then since it's an ether, we put, instead of ethyl, we put adoxy. Or you could call this or isopropoxy, or you could say 3-isopropoxy. So instead of propyl for an alkyl group, we say oxy to give you the ether as a substituent. Okay, and then our parent chain is cyclohexane. Okay. Now, if we were to assign priorities here, for bromine, 1 is alkyl group, 2 because it's closest to the ether, and 3 here for the other alkyl group. So we get that goes counterclockwise, right? So that's going counterclockwise. So this one's going to be S, okay? And then if we look at the bromine now, we have different color here. 1, 2, and then 3 here. So that's going, since the hydrogen's in the back, that's going clockwise in right here. So clockwise 1, 2, 3. This is R. So we could say cis. This can be or 1s 3r. So we won't be picky here. 1 bromo. 3-1 methyl hydroxy cyclohexane. Okay, so that's how we would do that second one there. All right, let's go over a different one. Now let's actually transfer. Let's go from a name to a structure. So say we have 1-1-1 trifluoro 7-methoxy 4-2-methyl propyl decane. Well, a long name, huh? And then 2-3-5 triol. All right, so when you name a polyol or alcohols with multiple OH groups, the indication has to come at the end, and there's no other exception. There's no other way. Okay, so let's see here. We have a decane. So let's draw a decane on our structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, drew a little bit. We drew 1 too many carbons. All right, so at the 1 position, we're going to draw 3 foreign groups. So this will be 1, 2, 3. Okay. And then at the 7 position, we have a methoxy, so that's going to be OCH3. So OCH3 here. So 1, 2, 3, 4, 5, 6, 7. So we have an OCH3 here. Okay. And then at the 4 position, we have a methyl propyl, 2-methyl propyl. So this is another name for pretty much isobutyl. Okay, so at the 4 position, we're going to draw this group here, and it's going to connect to it like that. So if we number them here, it'll be 1, 2, 3. Okay? And then lastly, we're going to draw in our alcohols here. So we're going to have an OH at the 2 position, 3 position, and 5 position. So we didn't mention stereochemistry, so you don't have to worry about any of that. So 2, 3, and the 5 position. Like that. And we're done. There we go. Okay, so that's how we do this nomenclature problem. All right, let's do a few more, just for good measure here. All right, now let's do something cyclic. We haven't done really something cyclic that includes like an ether. All right, this one, we have no choice. We have to sign R and S because there's more than two substituents on the ring. All right, so first let's number the chain here. So what number carbon should we be thinking about? Okay, so there's two ways to think about this. So since the carbon with the chlorine and methyl group is more substituted, we should probably number it where that carbon gets the lowest number. So let's number it. So first we number the oxygen because it's a heterocycle. So 1, 2, 3, 4, 5, 6, 7. So this is going to be a cycloheptane. Oh wait, no, sorry. It's going to be a cycloheptane here. And since it's not a carbon cycle, it's oxygen, we're going to put oxa in front of the cyclo part. So it's an oxacycloheptane, okay? So that's what we do for cyclid ethers. This one. There we go. Okay, so now let's think about the nomenclature here. So the substituents we have at the 4 position, we have chloro and 4-methyl. And then at the 6th position, we have 1, 2. So we're going to have 1, 1 dimethyl ethyl. Or 6-terbutyl. Okay. All right. So now let's go ahead and name this. First, let's assign again stereochemistry. So let's go to the chlorine first. So 1. 2, because this is closer to the oxygen group, and then and then 3 for the other chain here, closer to the terbutyl group. So this one is going to look R. So this is going clockwise again here, 1, 2, 3. So this is going to be R. And then we look at the second stereocenter. At the 6th position, we're going to see that this position closer to the oxygen group is 1. And then the terbutyl group is 2. And then lastly, the third group closer to the chlorine is 3. Okay, so this should be also clockwise. So this is also R. Okay, so our stereocenters, we have, now let's write the whole name, 4R, 6R, okay? And then we have 4 chloro, 6 dash, oops, 1 dash 1 dimethyl ethyl, dash 4 dash methyl, another methyl group here, Okay. Oxa, cycloheptane. Now that was pretty close to the edge there. Oops. So I don't know if I can fucking get to all of it. Here we go. Here we go. Here we go. So yeah, that's it. Yeah, pretty long name there, but you see here, not too bad. Just cyclo ethers. You put oxa in front of the ring size, the cyclo, and then yeah, you're all good. Okay, now let's do a few more here just for extra practice. So the level of difficulty you'd expect is something on this level or something shorter in length. Okay, so say we have this compound now. So this review, since it's kind of like a crash course, I'm going to simulate it like a actual length of an exam. So if you do take this, it'll feel like you're preparing for the exam by doing an actual exam. So it should give you a better sense of, how you stand. Okay, so all right, so here is our another ether, a very complicated ether here. You actually have, the only way to probably form this molecule is to make it. But anyway, let's first find the parent chain here. So the parent chain, if you have a linear ether and a linear chain, the number of the chain is going to the parent chain is the longer alkyl chain, okay? And then the other alkyl chain on the ether becomes a substituent for when the ether becomes a substituent. So we're going to find the longest chain first. And how we do that is, let's see here. Okay. So we're probably going to number in the way that gives us the lowest values for our substituents. It doesn't matter if the oxygen has the lowest number, and that's because it's not an alcohol, so it doesn't get really priority here. So we kind of treat the ether as an haloalkane or a halogen. So we probably want to number this way: 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then if we numbered it the other way, we would get positions here 4, 5, 6, 7. So we go substituent at position 7. So that would actually be the a higher number scheme. So we're not going to do that. Okay, so at the 1 position, so at the 2 and 3 position, we have a dimethyl substituent, so 2 methyl groups. And then at the 6 position, we see at this ether we have 1, 2, 3, 4. So that's going to be 6 butoxy. Okay, so it's going to be 6-butoxy for our substituent here. And then we have an octane as our parent chain. So we have an octane. Okay, so butoxy will come first, 6-butoxy dash 2, 3 dimethyl octane. All right, there we go. So that's how we name this ether. All right, let's do a couple more now. Okay, so let's do one more name to structure. All right, let's see what we have. So we have so if we look at our parent chain, we see we have an octane. So that tells us we have an octane. So let's draw an octane here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And at the 2 position, we have an alcohol. So let's just number it this way and put the 2 right here. So that's a 2 alcohol. At the 3 position, we have a methoxy, so that means an OCH3. Like that. And then at the 4 position, we have a bromine. Okay, so notice how I wrote these as planar bonds here with no stereochemistry. And that's because we kind of have to figure out first what it should be. Okay. So we notice that at the 2 position, this should be an S. The 3 position should be an R. And the 4 position should be an S. So what should the bonds be? So the best thing to do is to kind of assign the stereochemistry, you know, maybe give the OH a wedged or a dashed, and then go from there whether or not it should be a wedge or dash based on what the stereochemistry you get from assigning it. Okay, so first let's just make this a wedge bond. So that means the hydrogen is going to point towards the back. All right, so if we do that, let's number this in different colors here. Alcohol 1, 2 for the long chain ethyl group here, and then actually it might be best if I don't name it so close. So then 2 would be the group from the chain, and then 3 is the methyl group here. All right, so if we do that, that gives us a counterclockwise direction, but we want S, right? So we have to flip it. So it can't be this, so nope, can't be that. So we're going to flip it to get the opposite stereocenter. So we're going to make this actually a dashed. There we go. Okay. Now let's do the same thing for OCH3, but now this time let's try making this a dash instead. Okay, maybe that will work better. All right. So in this case, we're going to have the OCH3 number 1. The second group going towards the OH is going to be group 2, and then this group near the bromine is going to be group 3. Okay, so if we do this, the hydrogen is now pointing towards us. So let's assign the stereochemistry here. So it's going to do 1, 2, 3. So it looks like this, right? So it looks R, right? Oh, wait, no, it should be reversed. Sorry. Messed up again. Yeah, sometimes this always gets me. I'm always thinking that the bromine is less priority because it's less such a negative. So it has to do with atomic number. So don't forget that, okay? All right, so it looks like it's S. So it's going 1, 2, 3. So bromine has higher priority now than oxygen. So it looks like it's S, right? But the hydrogen's in the back, so we're going to switch it to R. So we are correct. So it should be a dash bond. There we go. Okay. Now that we have that out of the way, now let's do the last bond here. Okay. All right, so I don't know, for simplicity's sake, let's make this bromine dashed. Dashed. All right. So in this case, bromine will get the 1 position, and then this second group here would get the 2 position, and then the alkyl group will get the 3 position. So the hydrogen is pointing out at us again. So this looks like it's 1, 2, 3. Okie dokie. Let's see here. Okay. 1, 2, 3. So it does look like it's S, but is it actually R? Huh. Bromine definitely gets the 1 position. And then that gets the 2nd position. Yeah, I think it looks like it. All right, just give me 1 second here. All right. For S. Okay. Okay. So I know this should be S. Oh wait, sorry. It's definitely way too early here. So it looks like it's S, right? It looks like it's S, but in reality it's actually going to be R because we have to flip the stereochemistry. So we have to make this a wedge bond. Okay? So we're going to actually make this a wedge bond. So let's just color this in now. Way too early and a lack of sleep, I expect, in the coming days. Okay. All right. So this is our final structure here. The octane and it's an octanol. Okay. So let's do one last example. We spent quite some time on nomenclature already. So, but it's good in case we kind of forgot how to do these things. It's good practice. Okay, so one last example. You know, if everyone does this, you don't have to watch the whole video. That's why I kind of, when I make the video, I actually group it into sections on YouTube. So students can kind of go to the section they think they need, they want to review the most. And you don't necessarily have to do it all. Okay, so now we have this cyclic molecule here. So let's number our the parent chain here. So the most substituted carbon will get number 1. So the bromine, 2, 3, 4, 5. So we numbered the cyclopentane because it has more carbons than the cyclopropane. Okay, so we have 1 bromo. One bromo. 1 methyl. 1 4-methyl, dimethyl. And then at the 3 position, we have cyclopropyl. And our parent chain here is cyclopentane. All right, so at the cyclopentane, we're going to have 1 bromo, 3 cyclopropyl dash 3 dash cyclopropyl, one comma 4 dimethyl cyclopentane. All right, there we go. So that's 1 bromo, 3 cyclopropyl, dimethyl cyclopentane. Okay, so that's pretty much it for nomenclature, what we expect. So a wide variety here, but big emphasis on chapter 8 and 9, kind of new molecules you've seen other from haloalkanes. So we want to be able to kind of name those. Okay, so let's go on now to some concepts we should all know for the final. Okay. All right. So if we have a weakly basic nucleophile and a secondary alkyl halide, will generally get blank mechanisms which will involve transition state. All right, so let's fill in the blank and choose this multiple choice question here. So if we have a weakly basic nucleophile and a secondary alkyl halide, we'll generally get SN2 type chemistry. And then this involves so the most appropriate answer here is backside attack. Okay. All right, so we want to use that one. All right, so there's no carbocation rearrangement, and the transition state is not exactly anti-periplanar. That's referring to the E2 reaction. So that's when we get the anti-configuration of the 2 carbon atoms to give us the right geometry for the formation of the alkene and departure of the leaving group, like so. Okay. Next one, a functional group. A functional group with AR, CO, NH2 is a what? A functional group with a R dash SH is a what? And a functional group with C double bond C is a what? Okay. So let's try this one. So RCONH2 looks like this, right? Double bond O, NH2. So we know that as an amide. Forms the backbones of our DNA, okay? A group with RSH is a very smelly compound. So you might find this in rotten eggs if your eggs go bad. This is called a diol. A diol. Okay? And then when you have two R groups, we call that a diol ether. So it's very similar to an alcohol and ether because oxygen and sulfur are in the same chemical family. And a functional group with a C double bond C, as we know, is an alkene. Okay, there we go. So we want to know our functional groups here. And one thing I will mention is that remember that if we're looking for functional groups in IR, the strength of the frequency in IR is dependent on the strength or the strength of the bond and also of the two atoms composing the bond. So it's hard to rotate a bond if you have if the atoms are heavier. So for example, a CH bond is easier to vibrate than a CO bond. And that's because generally speaking, like an CH bond is easier to vibrate than an OH bond. And that's because, the less heavier the atoms are, the easier it is kind of vibrate. Like if you try to vibrate something that's much heavier, it's going to require more energy, just because the atoms are kind of like heavier, so it's harder to vibrate. It's kind of like when you have a pendulum, that vibrational motion, the heavier it is, the more energy it takes to kind of make it go back and forth. Okay? So kind of think of it like that. All right. All right, let's get back into selectivities to this kind of vocab here. Chlorine. Okay, let's see. Chlorine has a selectivity. Selectivity of of actually. Oops, I was supposed to actually put it as a blank. All right, let's do it this way. 5 dash blank dash blank dash blank. Okay. For tertiary, secondary, primary. And last one, primary. Primary positions. When halogenating, alkanes. Okay, so we pretty much only know how to halogenate alkanes. We wouldn't want to do this reaction if we have an alcohol present, and that's because you'll probably get reactivity with the oxygen that you can't control. While bromine has a selectivity. Bromine has a selectivity of blank to blank to 1. Oops, it's supposed to be 1 only. 1 for tertiary. Secondary. Primary. So a good study per thing to do is kind of, as you go through this video, kind of write everything down, so it allows your, kind of like brain to process this information better. But it kind of all depends what kind of learner you are. I'm more of a visual, and then active listener type learning. So when I learn, I kind of had to write good notes on the board, make sure I could take the writing notes is key, and especially helpful if my professor, or my instructor writes on the board and kind of talks the way through the lecture slides. So I'm really bad when it comes to just having lecture slides just presented to me, because in my experience, instructors, they go over that material way too fast. I don't have time to process it. So if that's the case, usually I have to read ahead of time. I also encourage reading material ahead of time to kind of understand what's happening in the lecture, and so you don't get lost. So there's different learning styles. I'm typically the active learner type, which means a lot of doing work ahead of time before going to class. But everyone's different. That's my recommendation. Okay, so anyway, primary. So that's one long one. If we wanted, to convert to dash methylbutane to 2-halo. So that's just a halogen, 3-methylbutane. Okay, with high yield. We should use all right, what should we use? Is it bromine? Bromine dash chlorine / a different halogen. Okay. So if we write out the structure here, it's 2-methylbutane, so we want this molecule right here. So we need to halogenate, we need to get, oh wait, is there, excuse me here. No, there's not. Okay, so we want to get the halogen now at the 2 position. So we want to get the bromine right here. Or sorry, the halogen right here. Okay? Alright, so what should we use here? So we want a secondary position, right? So if we use bromine, we're going to get on the tertiary position, so we don't want that. So we want something that favors secondary, so that's going to be chlorine. Okay? So if we ever have a situation where we want secondary over tertiary, you want to choose chlorine. Okay? There we go. Oh, I didn't answer the other ones. Oops. Alright, so chlorine has a selectivity of 5 to 4 to 1 for tertiary, secondary, and primary positions, and then bromine has a selectivity of 1700 to 80 to 1 for tertiary, secondary, and primary positions. Okay? Alright, now let's go to let's talk now about NMR dash in 1H NMR. A CH adjacent to a benzene. So we want to be familiar with these ppm, these frequencies of the type of hydrogens where they show up. And my best recommendation here is you do a lot of problems that kind of gets you familiar with all these types of hydrogens. I know, it's a lot to remember, but, UC Davis, it's tough here. And that's because they expect you to be the best amongst your field. And in this case, we have to test it like this. So it's going to be probably no, you're not going to get an NMR chart. So I will not rely on that, getting an NMR chart. So you really have to do these problems to prepare for any kind of NMR showing up on an exam. And it's good because you'll see this again time and time again in 118B and 118C. I can almost always guarantee that there's going to be something related to spectroscopy on every OChem exam, no matter the class. Okay. Organic, no matter the organic class, so 118B and C. All right, so a 1H NMR, a CH adjacent to a benzene will show up at is it 7 to 8, 5 to 6, 3 to 4.5, 2 to 2.5, or 5 to 0.5 ppm. And a CH adjacent to oxygen will show up at 7 to 8, 5 to 6, or is it going to be 3 to 4.5, or 2 to 2.5, or 5 to 0.5 ppm? Okay, so what is going to be? So I'll just tell you what these peaks are. So this is benzene. So it's not going to be that. It's adjacent to a benzene. 5 to 6 is alkene. 3 to 4 is, so this one, CH adjacent to a benzene. It won't show up to 3 to 4. That's actually this one. CH adjacent to oxygen. That's going to be 3 to 4, 4.5 ppm. So let's just circle that one right here. That one, okay? So those are indicative of having an oxygen in your molecule, because you'll have a peak here. Well, hydrogen's nearby. That tells it it's it's relatively downfield. Okay, and then 2.5, 2 to 2.5. That means you have something adjacent to a double bond. So a CH adjacent to a benzene is going to be a double bond situation. So you have a benzene here. And here's my hydrogens I'm talking about. So let's just say this is R. Here's H. So this is going to be next to a double bond. So pretty much the same thing kind of applies. So the same thing applies to C double bond O and C bonds. When you have things adjacent like that, they tend to be at the 2 to 2.5 range. So these are all adjacent to the 2 to 2.5 range. So we're going to circle this one right here. And then this last one, 5 to 0.5, that refers to a hydrogen bonded to an electronegative element. So it could be X equals oxygen or nitrogen, usually. Okay? And that's because these hydrogens, when they're attached to electronegative atoms, they can hydrogen bond to other molecules, other similar molecules in solution, and that causes the frequency of the H to be variable. So it's kind of like what you saw in IR, that it just didn't, the OH bond just didn't occur at 3400 as a sharp peak. It's kind of broad between a range of frequencies. So it's kind of the same thing in NMR too. Okay, so that's a little talk there about NMR. Let's move on here. Okay. All right. Let's talk about cycloalkanes. Cycloalkanes live exactly two substituents can be considered cis or trans. All right, cis or trans. Cis or trans. Okay. Oh, shoot. I was supposed to put this as a selection. But anyway, we know cis or trans, right? It can't be 3 or more substituents. It has to be 2. That's why in the nomenclature question, we said it could be 2, or it had to. We could say it was cis. We could say cis or specify the stereochemistry. That's fine. Linear alkanes. All right, so when we have linear alkanes, they can or cannot be cis or trans. or trans because they can blank. So oftentimes when we see these types of questions, you don't have a word bank, so you would actually have to recall the stuff you studied to actually answer these questions. Okay, so can linear alkanes be cis or trans? So think about this situation, right? We never say 1,2-dimethyl trans or cis dimethyl like octane, right? And that's because there's nothing to restrict these bonds from kind of like interconverting between going in the back of the page, a wedge bond, and going to the front or pointing out at us, or having a wedge bond, right? And that's because, these molecules, when they're linear, there's no restriction of bond rotation, so they can rotate. And we saw that for conformers, right? So we saw that these groups of substituents, they can rotate rapidly, so it wouldn't matter if it's going in the back of the page or the front of the page. There's no form of the molecule that can stay cis relative to another substituent or trans, so it's not possible. So we say cannot. They cannot be cis or trans. And kind of just think about that. Back in your notes, how you learned all these naming, you never see a cis or trans for a linear alkane. If we want to specify the stereochemistry, we have to actually write R and S. Okay. All right. All right, let's talk about some stereochemistry. Good segue there. To be meso. So think about meso compound. To be a meso compound. Well, that's not rather that. Sorry. To be meso, a molecule. Okay, a molecule must have at least 1, 0, 2, 3 stereocenters and will usually have R/S/R/R /S/S or R/S, comma, SS. Oops, I already put that. Let's kind of backtrack. Sorry, everyone. Let's backtrack here. R-R, R-S, SS /R/ comma S/R configuration. Mesomolecules. So mesomolecules. All right. So mesomolecules are, or are they not, optically active? optically active, and do or do not contain an internal mirror plane. All right, let's go through meso molecules. So remember, to be meso, a molecule must have at least 2 stereocenters. It can't have 1 or 0. It won't have form a meso compound. So the thing about meso compound is that it looks chiral, but it actually is not chiral because it has a plane of symmetry that makes it optically inactive. All right, and the key here is that you find 2 stereocenters with exactly the same type of substituents as the other, but they'll usually be right next to each other, and they have an alternate configuration. So R to S, S to R, going in our direction. So it's going to be R to S, R comma S. Okay. And then we say they are not optically active, okay, because they do contain an internal mirror plane. Okay? Good. All right. Now, we were talking about IR, I think, a little bit before, so now let's go over that now. Okay. And C double bond O has a peak at about is it 2700? Is it 2750? Is it 2200? Or is it around 1700? Or 1640? In the IR. While and CC triple bond has a peak at, is it 3300? Is it 2750? Is it 2200? Or is it 1700? Inverse centimeters here. Okay. So our C-O, the characteristic peak is at 1700, so make sure we know that one. And then the triple bond is at 2200, right? The CC bond. So it's not 3300, that's the C triple bond CH bond of an alkyne. So let's not forget about that. Okay. So one thing to also consider is also know like the order of kind of the types of bonds, which ones has high frequency, low frequency, be able to kind of interpret like be able to like kind of arrange the bonds from high wave number or high frequency to low frequency in increasing and decreasing order. So that's also a question we might ask. That's also relevant. Okay. All right. Let's talk a little bit more about radical reactions. In radical reactions, Okay. Blank. Blank steps from radicals sorry, that shouldn't be that. It should be form radicals. Steps, blank steps form radicals, okay? And are always, or is it sometimes? Or is it never endothermic? So propagation. Oops, sorry, nope. But I can't tell you the answer, did I? Blank steps exchange. Okay, what do they exchange? They exchange something. Exchange radicals. And are always, sometimes, or never endothermic. And termination steps. Oops, said again. My bad, everyone. Blank steps remove radicals. Remove radicals. And are, is it always? Always. Sometimes. Or never endothermic. All right, so let's think about this. So remember, in radical reactions, initiation steps, form radicals. They are what form the radicals, and they are always endothermic. You can't just form radicals in room temp. To really get this reaction going, you need to put in energy. So they are always endothermic. So propagation, the next one is propagation steps are what exchange radicals between between species. And they are sometimes endothermic. So in the exception, if you remember, most of the time they sometimes, usually the first propagation step is endothermic, right? But sometimes they can be exothermic, like in the case for fluorine, and then, well, not fluorine, but like maybe I think bromine, and I think iodine. Remember, iodine's one of those exceptions where it can't substitute because of the endothermic step of the second propagation step, or if you kind of recall that one of the two propagation steps are endothermic. So it's sometimes endothermic. And then termination steps, they are always exothermic. They are never endothermic. They remove radicals, and when we end a radical cycle, that's a favorable. That means the reaction's over, and radicals, they do want to come together and form a bond because they're missing an electron. So they rather form bonds. So termination steps are never endodermic. All right. So almost done here with these concept questions. All right. Let's talk about oxidation. So oxidation in organic reactions involve loss of so we say so we're gonna write our answer here, or gain of bonds to blank atoms. Okay. So remember in organic chemistry, oxidation pretty much refers to the loss of hydrogen. So I'm going to say H2 or electrons slash electrons, okay? Or electrons, like there. Or you could say it's the gain of bonds to electronegative. So let's say electro. Or we could say slash oxygen atoms. So remember, when we go from an alcohol to a ketone, we're losing H2 or electrons from the hydrogens to form a double bond to the oxygen. So we're forming more bonds to C double bond O. So you can kind of think of it like this. So here it represents oxidation here. And see, we're getting this molecule here. So for more bonds to oxygen, plus H2 is lost. Okay? So it's not, you don't produce H2 gas. So there's kind of a misnomer there. I'm just saying the total number of atoms lost is 2 hydrogens. So you get a, so 2 hydrogen atoms are inevitably lost. So this means 2 H atoms removed from the compound. Okay? All right. All right. Next. Now we say, all right, which of, all right, let's see here, which of each pair all right, which of each pair will have a higher, all right, good, will have a higher boiling point? Okay, so which one will have a higher boiling point? Let's think about it. Methane versus butane. Octane versus octanol. And then pentane versus neopentane. Okay. So neopentane looks like this, where this is the R group. And pentane is just regular 1, 2, 3, 1, 2, 3, 4, 5. Octane, 1, 2, 3, 4, 5, 6, 7, 8. And then octanol, looks like that. Okay, and then methane is CH4 and butane, like that. Okay, so in general, the more carbon atoms you have, the higher the boiling point, because there is more London dispersion forces. And we kind of recall back to intermolecular forces, so butane would win in this case. Octane versus octanol, so this has hydrogen bonding, OH bonds. OH bonds. So we have hydrogen bonding, H bonding. So when we do that, that gives us a much stronger intermolecular force. So octanol will have the higher boiling point. So that's why water exists as a liquid and not as a gas, is because of hydrogen bonding. And lastly, we have pentane versus neopentane. So remember, if you recall in alcohols, the less branched you are, so the more branching you have, it tends to be that you have the lower boiling point, because you can't interact with molecules of similar molecules because there's steric hindrance. So we kind of think about these molecules here. Let's just say, let's see, 1, 2, 3, 4, 1, 2, 3, 4, 5. I actually forgot what neopentane looks like. Let's see. I just want to make sure I'm drawing it right. Oh, yeah. So neopentane is actually looks like this. It's another name for like the tert-butyl variant of as a carbon compound. So it looks like this. So this is neopentane because now it has 5 carbon atoms. But you see here, you know how these are all CH3 groups. So it's kind of hard to interact here. So we think about it. 2 pentane molecules, they can kind of like interact like this. They can kind of stack up. They can stack up towards one another. And so there's more surface area. So more surface area. And that usually means stronger, more surface area equals stronger forces. Stronger forces and higher boiling point. So we get a higher boiling point. Okay? But if we think about this tert-butyl group, right, they can really only interact like through this kind of interface here. So there's going to be less surface area. Less surface area, and it's going to be weaker intermolecular force. Okay? So that's why pentane would win in this case. Okay. Ironically speaking, neopentane will have the higher energy content. So you get more energy from neopentane just from pentane. That's why if you look at octane for gasoline, usually the rating for gasoline are based on the isomer of octane, methyl octane or isooctane. And that's why in gasoline, usually we have branched hydrocarbons, cyclic and branched cyclic hydrocarbons. So the more kind of branching or connectivity you have to the carbon atoms instead of hydrogens, it actually releases more energy. And that's because you have more CC bonds. Yeah, so usually you have Well, it's not just more CC bonds. That's actually kind of misleading. What you have is pretty much more branched carbons, and there's something about branched carbons that give them a higher energy content, and it probably has to do something with intermolecular forces as well. But in terms of boiling point, though, that's actually a little bit different. There's a different trend for that. Okay, but don't worry too much about energy content. What's important is boiling point. Okay. Now let's go over. Let's go over some more things about a little bit about energy. So, when forming a cyclic ether, right? So what controls the ring formation? So blank favors small rings. Actually, let's just kind of separate here. Small rings, and blank favors rings with minimal strain. Whoops. Okay. In this case, then, so 3/4/5/6 member rings are the easiest to form, are the easiest ring to form. And then this is followed by 3, 4, 5, 6 member rings. So we're thinking about the order here. Which ones are easiest to form? So when forming a cyclic ether, right? What favors small rings is entropy, because the formation of the ring is easier because the leaving group and the oxygen are closer together. So it's easier to form if you have a situation like this. Okay, because it's closer. You don't have to kind of rearrange the molecule as much to get entropy favorable. So entropy favors disorder. So the smaller the ring system, the less ordered the ring is in terms of getting the atoms neatly in a ring. So it's faster for three-membered rings. Okay? And then enthalpy favors rings with minimal strain because you have, in total, there's lower entropy of the system because there's less ring strain. So in this case, enthalpy will favor rings with minimal strain. So larger rings are more ordered, so they're not favored entropically. But remember Gibbs free energy. So Gibbs free energy, delta G equals delta H minus T delta S. So we have both an entropy contribution and enthalpy contribution. So the formation, or the delta G, the relative favorability of forming these rings are dictated either by enthalpy, is Is it entropy? Is this formation driven by enthalpy, or is it driven by entropy? So there's two kind of factors to consider here. And so that's why we say entropy favors small rings, enthalpy favors the ring with less strain. So that's going to be larger order rings. So three-membered rings form the fastest because they're easiest to form because they're closer to the site of reactivity there. And then the next fastest is the five-membered ring. So four-membered rings, they're kind of in the middle. They're too far. They're too far for entropy's sake to kind of favor formation, and they're too strained to be considered enthalpically favorable. So they tend to not be very favorable in forming. So they're really hard to form. Like cyclobutanes, not really seen much. But you can form them, but they are difficult. They're not favored if you can form a three-membered ring or a five-membered ring or six. All right. Lastly, let's talk about now let's talk about electrophiles and nucleophiles as our last kind of thing here, and then we'll go into some short answer questions. All right. An electrophile donates does it donate H plus? Does it accepts H plus? What does it do? Donates electrons, accept electrons, or does it do accept electrons? Okay, and they will is it always blank sometimes or never have an empty orbital? Okay. So this is the first part. Electrophile, remember, electrophile is an electrophile in general accepts electrons, right? They accept electrons to form a new chemical bond. So this can be from an SN2 reaction where the electrophile accepts a new bond forming from the nucleophile, or it can be from like an acid-base reaction where the hydrogen accepts electrons from a nucleophile from a base and departs the molecule. But in this case, in generally speaking, we can say all electrophiles, they accept electrons. Okay, and they will all sometimes be empty orbitals. So for example, you can have a carbocation has an empty p orbital, or you can have a metal that accepts electron donation from another ion or molecule. So it sometimes have an empty orbital. But electrophiles can be alkyl halides where there's still a filled orbital, but there's charge separation in the molecule. Okay. Now, electrophiles are always, are they always Sometimes. Or never. Lewis acids. While Lewis acids are blank always, sometimes, or never electrophiles. Okay, so some things to consider here. Electrophiles, they are sometimes Lewis acids. So for example, a carbocation is a Lewis acid. It can accept a pair of electrons to donate, but if you have something like a bromide, right? It's an electrophile, right? But carbon has 4 bonds, right? So it's not a Lewis acid. So that would be a situation where it won't be a Lewis acid, okay? But all Lewis acids are electrophiles, are always electrophiles, because they can accept electrons, okay? So it's kind of like what we said about nucleophiles and bases, and stuff like that. So we kind of have to think about electrophiles in kind of the same way. All right, let's move on here. Enough of kind of vocab there. Alrighty, so let's just use some values here. So here we're going to assign the pK. We're going to be given some pKa's here. So here are some pKa values. So knowing these pKa values will make OChem a lot simpler if you kind of can master these. So -10, -3.8, -2.2, 0. Okay. Oh, sorry, it wasn't 3.5, it's 3 to 5. 9 to 13. 12. 16 to 18. 25. 30. 36 to 40. 38. And then we have 44 and 50. So, you don't have to memorize pKs for the series class, but it might be helpful to rationalize like what's more sick than something, like what has a higher pKa or a lower pKa. Okay, so let's assign these pKa's here. So this hydrogen. So we're looking at this hydrogen. Okay, so what should the pKa? Oh wait, not that one. So what should the pKa be for this? Okay. So remember, carboxylic acids are acidic, so their pKa's are usually 3 to 5, so they're weak acids. And that's because the oxygen atom gets negative charge, so there's a more stable conjugate base relative to other molecules. So here's 3.5, 3 to 5. All right, how about this tert-butyl protonated alcohol. Okay, so when you have an oxygen, when you have an oxo acid, so an oxygen-based acid like OH, and it's protonated, that's a very strong acid because it wants to get rid of the hydrogen so it can become neutral, which is more stable. So this will have a negative value, so it's around negative 3.8. Okay. And that's pretty much something you kind of just have to know, honestly. So because it's hard to differentiate negative 3.8 to negative 2.2. So it has to come on a case-by-case basis. But just know it'll be negative. That's pretty much all you need to know for this class. So usually they are negative. So now we have a trifluoro group, CH2, OH. So remember, when we have an electronegative group next to an alcohol, it's going to be very acidic. It's going to decrease the pKa. So just kind of remember, alcohols are near 16 to 18. So if you have electronegative atoms nearby, it's going to be less than that. So in this case, we're going to say 12. Okay, so somewhere near 12. All right. Amines are not very acidic, and that's because when you deprotonate them, they become very good bases. So their pKa's are going to be in the range of 36 to 40. Okay. And then you probably recall alkanes. They're not very acidic at all. So let me just point to the hydrogens I'm talking about. Okay, because we have to consider the hydrogens. Okay, so alkanes, this is a number you should know. Alkanes are they're the hardest to deprotonate. And so they're always near 50. Okay, so alkanes are not very acidic. All right, now we have diols. Diols are more acidic than alcohols because of the sulfur, so they're going to be less than a typical alcohol, which is 16 to 18. So they are usually between 9 to 13. And we think about hydrosulfuric acid, H2S, that pKa is like around 10. So you kind of think about like, around the 10 to 12 range or 13 range. That's pretty much the pKa for a diol. Okay? And then we have HI here. So it's almost impossible to arrange the pKa's or the acidities of these compounds unless you know the values. So remember, HI is a strong acid. So out of all of them, they should be the strongest. So we're going to say negative 10. But this exercise is just trying to rationalize these values and kind of think about why some are more acidic than others. Okay, alcohols, they're like water. pKa water is 15.5, a value we should memorize. So it's about 16 to 18. All right, so just think about so in terms of pKa's, just think about that. But the series class, we don't worry too much about memorizing pKa's. What's more important is if you can put these compounds, if I gave you a handful of these, put them from most acidic hydrogen to less acidic hydrogen, or increasing pKa or decreasing pKa. All right. Let's try some more. All right. So let's not forget about bond line. So I would say at this point we should be comfortable drawing structures like from condensed to bond line, but it's okay if we're not yet. So always, when I say always, always be familiar with the different structure types, because you may see a lot of them in your studies here. CH2, CH. All right, that's a pretty long compound. Let's see if we can do it. All right, so we have two isopropyl group, two methyl groups, CHCH, and then CH. So that's the CH2, 5 of them. 1, 2, 3, 4, 5. And then we're going to have a double bond O connected to an oxygen, so an ester, CH2. Then we have an alkene here. Oops, I'm actually a 1 carbon off. 1, 2, 3, 4, 5. Here we go. So the one O, oxygen, CH2, alkene, CH. So when we have two CH compounds next to it, it's usually an alkene, but it can also be something substituted. But we don't have anything substituted, so it has to be an alkene. Then we have a Br here, sticking out here. Oh wait, I forgot the CH2. So it's always good to kind of, when you have large molecules like this, make sure you double check everything. So CH2, then we have the alkene here. Then the bromine is going to be branching out. So sometimes bromines will be in parentheses, but sometimes it will not. So just be aware of that. Then we have CH, and then branching out is an ethyl group right there, and then CH, a methyl group on the adjacent carbon, and then two CH2 groups, followed by an aldehyde, not an alcohol. Like that. Okay, I think that is it for drawing the bond line formula. Okay. All right. Okay, so almost up to our mark here, but don't worry. I think this will be a good review for students who are kind of need some more kind of guided practice. Honestly, if we had a big lecture room, I would just hold this in person, but it's okay. All right, so let's look at these molecules and answer the questions, okay? So let's draw a few of them here. So here's molecule A. Here's molecule B. Wait, let me just erase this a little bit, just so I have some room here. Okie dokes. So let's point to this hydrogen. and this hydrogen. So this is structure D. All right, so the first thing we do is we're going to say how many different chemical environments in this case, this is an alternate way of saying number of peaks would you expect to see? Expect to see in the 1H NMR for each molecule. Okay, so what do we see? Let's go with A. Let's count the number of peaks here for A. So these methyl groups here, they will be 1 because they're rotating. They're all methyl. All the methyl protons will only see one signal because they're they're equivalent by rotation. 2 for the CH2 groups on the left. 2 for the CH2 groups near the oxygen, and then we have 4 for the CH bond there, and then for the 2 methyl groups there, it's going to be a 5th signal, so expect 5. All right, how far letter B? Starting to get my hand's starting to cramp up. Okay, so B. So we have pretty much 3 equivalent ethyl groups, right? So we're going to have 1, 2 for the CH2 groups, and then the CH group is going to be our third peak. So everything else is chemically equivalent by rotation, so only 3 signals for B. Because they're all ethyl groups, right? They're all the same ethyl groups. Okay. All right, let's look for C. So C here we have a mirror plane. If we kind of draw imaginary plane of symmetry here. So that means so the plane of symmetry pretty much means that there's only a plane of symmetry going down the molecule. So what happens is that you only get the hydrogens on the same face of the cyclohexane are equivalent, not the 2 hydrogens on the same carbon in the ring. So we're going to illustrate that by saying here's 1, and then we get 2, 3, indicating that the top and bottom hydrogens are different signals, and that's because they're not equivalent horizontally. So they can't be actually they're not the same signal, just like we saw for rings. 4, 5, 6, and then for the ethyl group 7, 8. Okay, so in this case C will see 8 hydrogens. All right, how about lastly for letter D? All right, so we have 1 for the aldehyde, And then this is not symmetrical, so we're going to actually see a few different hydrogens here. 2, 3, 4. OH will have a hydrogen, 5. And then 6 for the CH group, 7 for this methyl, 8 for the CH2 of the alpha group, and then 9 for the terminating CH3 group. So we expect 9 signals here. So when there's no symmetry, you have to count all of them. Okay? And then remember, like usually for straight chain alkanes, if you have multiple hydrogens on the same carbon atom, they're usually equivalent by rotation and then by just by mirror points in general. But it's usually by rapid rotation because the hydrogens are rotating, so they tend to have to give the same signal. That's why in methyl groups and CH2 groups, you don't see 3 individual hydrogens. You actually see one big peak for 3H or 2H. Okay? All right. Now there's actually a part B to this, so let's now do predict how many subpeaks So by subpeaks, we mean the splitting pattern would be seen. Be seen in the signal for the indicated hydrogen. So this is when I drew those arrows. So we're going to think about how the peak will look like due to splitting. For the indicated hydrogen due to spin splitting. So this is also called spin-spin coupling. Or, you know, how the spins kind of interact with each other through chemical bonds. Okay? All right. So let's go from top A. All right. So I'm pointing at this hydrogen. So I'll mark some now different color. This hydrogen. So it sees. So for spin-spin splitting, you're looking at the adjacent carbon atoms. And looking at the adjacent carbon atoms and how many hydrogens are next to those hydrogen atoms. So we have 3 hydrogens here. 3 hydrogens here. But it's also connected to these 2 hydrogens. So that's going to be 8 neighbors. So we're going to use n+1 rule. N equals 8. 8 plus 1 gives us a multiplet that should have 9 peaks. 9. All right, let's go back to letter B now. All right, we're pointing at this hydrogen in letter B off the CH2. So it's going to be connected to 1. So for linear alkanes, we don't consider splitting from any other hydrogen that is attached to the carbon atom for the hydrogen that we're looking at. So we don't consider coupling from like hydrogen atoms bonded to the same atom as the hydrogen in question, because we assume they're chemically equivalent, so they don't actually couple each other, so they don't see a different environment. So we have 3 from the methyl group and then 1 from the CH group nearby. So we're going to see 4 neighbors plus 1 gives us a 5 peak. Okay, like that. All right, letter C here. So letter C, we're looking at the hydrogen on the bottom of the ring here. So, so let's assume, it follows the n+1 rule. So it's like what you would expect. Okay, so we're not really thinking about complex splitting here. So we look at the neighbors here. So we have 1, 2, and then 3, 4, and then right here 5 and 6. So it's bonded to 3 different neighbors, which each have 2 hydrogens each. So that's going to be n, using the n+1 rule, that's going to be 6 plus 1. And that's going to give us a 7 peak. Like that. All right, lastly, letter D. All right, we're looking at the aldehyde. So the aldehyde has no hydrogens here, so there's no hydrogens. So no hydrogens here. So it's not going to be split by anything. So this signal should appear as a singlet or 1. So only a 1 peak. Now, if that aldehyde was attached to a linear alkane, so a CH2 group or CH, you will see splitting. So you definitely see splitting. And one other thing we should consider, if you have an alkyne like this, so these 2 hydrogens here, you can observe splitting here. So you do observe splitting here, even though this carbon right here, this carbon has no neighbors. You do observe splitting here. So this one would look like a doublet. And this hydrogen here would look like a triplet. So this is kind of weird in terms of the neighbor example. The alkyne is so short that the hydrogens can see each other through a neighbor that is not attached to the adjacent neighbor. So that's an exception here. Okay, so that's one of the exceptions that we see for splitting. So the alkyne the bond is so short that these 2 hydrogens, even though they're more than 3 bonds away, they can actually interact with each other. Okay. All right, here. Okay. All right. So yeah, this video is probably gonna be long just because of the fact that it's a final and not a midterm. So let's just get through it here. It'll be good. So I was planning on going over mechanism questions, but you won't need to really worry about producing the mechanism, I would say. So I wouldn't focus on it on that. I will focus on knowing your reactions, and for the sake of actually knowing the actual mechanism and predicting it on the exam, since we're some special circumstances, I probably won't go over that because that'll take a little bit too long here, and I do need to get to campus at some point. Okay. So now let's determine but I could just do one mechanism. It's fine. an appropriate one from chapter 8. Determine if the following following pairs of molecules are constitutional isomers. So my iPad is getting kind of slow. I think it's because it's overheating. Are constitutional isomers. Or maybe it's just my pencil. Are constitutional isomers and enantiomers. Diastereomers. Diastereomers, the same meso. Or chiral identical molecules. All right. I think some molecules will be familiar, but let's just do this one. All right, give me a sec. Let me get a swig of water. All right, so what are the relationship between these two? So if you kind of think about this, if you move this structure to the bottom here, they look like the mirror image, right? Right, it looks like the mirror image of the molecule on the left. So these are enantiomers. So you actually don't need to do anything in terms of assigning R and S, but to be safe, you can do that. But I'm just saying, there's some neat tricks you can actually do to kind of save you some time. So just something to think about. All right, so these are enantiomers. At first, I thought they were identical, but then I kind of looked at it again. If you try to superimpose them, they actually won't superimpose. So they're enantiomers. All right. So always in terms of these questions, don't always double check your answers. Okay. So here's letter B. All right. H3C. Sorry, I have a tendency to write too far or not make my bonds connected to the atoms. So these are called Fisher projections. They'll become increasingly important, especially if you venture into biochemistry. And when you go to 118C, you'll use Fisher projections to depict sugar molecules. So one of the most important molecules in biology, and then also amino acids, the molecules that give us our DNA. Well, not our DNA, sorry, our proteins. DNA are they're from nucleic acids. Oops. Okay. Give me 1 second. My alarm's going off. Okay. All right. So now we're at OH here. Okay. So now, what's the relationship between these two? Let's see, how do we think about this? So we think about these things here. So the relationship between the first stereocenter here and the stereocenter on the right here, it looks like the molecule was just rotated, right? Because all the positions on the first stereocenter are the same, are switched. So it looks like this one, so we look at this, see here, these substituents on the first carbon, the first asterisk there, all the substituents are changed, so the stereocenter stays the same. So we can eliminate enantiomers. Now, they are not the same compound because they're not meso. Because if you look at the structure on the left, the H and CH3 are switched. So that means the stereocenter should change on the bottom carbon. So, but we can actually assign priorities here. So we don't have to worry about the first one because we know the stereocenter is going to be the same, so it can't be enantiomers. And that's because all substituents are switched here. So we do the second one here. We have 1, 2, and then 3 for the methyl. And the hydrogen is on this line here, so that means it's dashed. So these bonds mean it's dashed. Okay. And then the bonds on the right and left are wedged. Okay, so if we do that, we get the right, we don't have to switch the orientation here, so it's S. Yeah, 1, 2, 3, S. And then if we look at the priorities here, we have 1, 2, 3. But this time the hydrogen is wedged. So this one will be S. And now if we look at here, we're going to see that it's in fact going to look like it's S, right? But it's actually R. So yeah, so in this case it goes from S to R. And we know the first stereocenter is going to be the same, right? Because it didn't change. So this is diastereomer. This is diastereomers. let me do something really quick. Okay. All right, so let's look at, let's do one more example here. Okay. Let me just do something really quick. Okay, sorry about that. Now let's go over the last example here for this section, C. Now we have okay, so this example, it looks like there may be stereoisomers, but if we think about the molecule, right, there's a mirror plane in the middle of these molecules. And if we rotate these molecules 180 degrees this way, we get the same compound. And since there's a mirror plane, we get it's meso, so it's a meso compound. Okay, so yeah, that'll be it for kind of determining the relationship between stereocenters. Okay, now let's go over either or. Okay. So in this one, we want to, for each of the given pair of molecules, okay, we're going to circle the one that is more stable. Okay? But we're also going to give a brief A brief phrase describing oops. Yeah, my iPad's getting really slow today. I don't know why. Probably a lot of writing here. Describing the chemical principle that makes it more stable. All right. All right, here's an example. Equatorial substituents okay, have less steric hindrance. Okay, let's begin. So here's my chair. Okay, versus so which one's more stable in this case? Cis, well, they're pretty much the same thing. I think they're just well, no. So it's very much the flipped version of the flipped version of the chair flipped. All right, so which one's more stable? We're going to circle the one with the larger group in the equatorial position. So we're going to say large group is equatorial. Equatorial, so we say, or you can say less steric hindrance. That's fine too. Okay. All right. Next, let's talk about carbocation stability. Plus versus here. Okay, so which one is more stable? Remember, primary is less stable than secondary, which is less stable than tertiary. So in this case, we're going to say this is a tertiary carbon versus a secondary, so it's going to be more stable. And why is it more stable? We have greater hyperconjugation. So remember, conjugation is stability of electrons or charges based off of exchanging double bonds for single bonds. Think of hyperconjugation as the kind of the same thing as resonance. So remember, resonance is what we kind of thought about in terms of stability of when we're drawing resin structures. But in here, hyperconjugation, think of it as we have that same kind of conjugation, but just between single bonds. So it's an interaction between a filled orbital and an empty orbital through sigma bonds. So that's called hyperconjugation. So we actually get more stability here because there's more carbon groups. There's more electron donating groups, carbon groups. Carbon is not electronegative, so it likes to release electrons. And that's why we say greater hyperconjugation. Okay? So greater hyperconjugation in this sense. All right, now let's take a look at some Newman projections. We shouldn't forget about Newman projections here. Okay. Okay. All right. Versus this Newman projection. All right, so which one is more stable? Well, one of them is gauche, so there's a steric hindrance between two carbon groups, and then the other one is anti, where the carbon groups are further apart. But you can't say anti. You have to say the reason why anti is more stable, and that's because less steric hindrance. Less steric hindrance, or so you could say steric interactions between the two carbon groups. But you want to say something along the lines of that. Less steric hindrance. Okay. How about, now let's talk about alcohols a little bit. The conjugate base of alcohols, the alkoxides here. Versus O minus. So which one's more stable? So we're talking about these things in solution. So which one's more stable? As probably a conjugate base. And it turns out that this one, the linear form, is more stable because you have greater solvation from water. So greater solvation. Okay, so usually the linear alcohol is more acidic, and that's because it has greater solvation in solution. All right, let's roll another chair here. Versus, all right, so you might think, oh, these compounds are the same, but it's all about conformation. So this is chair, and this is planar. Okay. So which one's more stable? So when we talked about cycloalkanes, we said the chair is more stable, and that's because if we drew Newman projections for each type of bond, all the bonds are staggered. But in the planar form, all the bonds are eclipsed. So this one will be the planar structure is the eclipsed form. The chair structure has we're going to say staggered bonds. So one thing we could say is less ring strain due to eclipsing strain from hydrogens in the ring. So less ring strain. less ring strain, or we could say bond angle strain. Or like I just said earlier, eclipsing strain. That's probably my favorite one to use, eclipsing strain, because the hydrogens now are all eclipsed. Are all staggered in a chair. There we go. Okay. All right, last one here, and then we'll move on here. And well, this is taking a long time. Damn, I didn't anticipate this. I should have did this last night. I just stayed up, but I was kind of too tired because I was also grading some papers. Oh well, like lab reports. Okay, say we have ethane and we have the eclipsed version here. Versus, well, this is kind of an extension of the last problem. But these concepts do become important if you ever go on to into higher orders of chemistry, higher classes where you learn about selectivity in reactions, and is often due to these kind of torsional interactions. So which one's more stable? Is it the eclipsing form or is it the completely staggered form, right? So we learned that it's the staggered form, and that's because there's less torsional or eclipsing strain due to the electron clouds from the CH bond overlapping each other and having a unfavorable repulsive interaction. So this one will have less eclipsing slash torsional strain. So torsional strain, torsional means the bond angle between the two carbon atoms, the angle between the two groups, the angle of, the angle pretty much at which at which you see how two groups are kind of how far they are from each other in space. That's torsional strain. Torsional refers to like a dihedral angle, if anyone knows what that is. So pretty much, if students are confused about what torsion means, it's like this. So what we're kind of doing is measure. So say I have two hydrogens here, right? So I'm measuring the angle. So I'm measuring this angle here. So I'm pretty much measuring, if these two were hydrogen atoms, right? I'm measuring the angle between these two hydrogen groups. So I'm measuring the angle between, well, maybe I should spell it. So torsions, equal angle between atoms on two adjacent atoms. Carbon atoms. So right now, these two look like they're close together, right? So this is actually a torsion of 0 degrees. So kind of think about this angle here. It's 0 degrees. And then when I go to a completely staggered relationship, the angle between here is 180. So that's what we mean by kind of torsional angles. The relative distance between these two atoms on two adjacent carbon atoms. All right, that was enough concepts, man. Let's get into reactions here. All right, so we're just gonna go from the get-go here. All right, we're just gonna do reactions because we are running out of time. Okay, so you know, for reactions, draw the major organic product, including correct stereochemistry, and we're going to assume all reagents are present in excess. So we have first tert butoxide, potassium tert butoxide, and tert butanol. So everything on the bottom usually refers to the solvent, but we can flip it around. So just be aware of that, especially on the last exam. So what would a product be, right? So this is a strong base. So it's strong base and bulky base. So we're going to favor E2 conditions, E2 chemistry, E2. And then there's only one product we can get. So we're going to favor the alkene right here. All right. Epoxide time. So this looks like sodium dialate and DMF. So this is SN2-like conditions. So we're going to open the epoxide in an SN2 fashion. So if we kind of remember here, remember SN2 favors the least hindered substrate. So we're going to attack the epoxide in this position. And since it's SN2, we will get SN2-like conditions. So we're going to write the product like so. Or now we attack from the backside. So this methyl group is going to point up, out, and up from us. And then we get the alcohol now pointing the other direction. Like so. And so see here now the stereochemistry didn't change at the other carbon because we didn't react at that center. Okay? Like that. So there's another way we could draw this if we want to make the sulfur look like a substituent. So we can actually rotate it. Where now, yeah, so it looks like this. You have to rotate it, but just make sure you maintain the same stereochemistry and you should be okay. But any I would say any form is fine. I don't mind. Okay. So SN2-like chemistry. So epoxide is pretty much like a good leaving group. And that's because even though the leaving group now is negatively charged, the reason it can do this is because it's probably because it can the ether, the ring strain causes in this case to be a good leaving group into O minus. So usually remember hydroxide doesn't want to leave because it forms O minus, but in this case it's favored because it's reducing the ring strain. And I'm guessing the proton, you get a proton from another SH molecule. That's probably what happens. So you get this molecule. So first you go to this. Then remember, everything is in excess, right? And so you probably go to here first. O minus. And you know, there's an SH molecule here. So it probably can pick up this proton and you form S2 minus. Like that. Okay, but it'd probably be better if we said something like this: 1 and 2, a workup, because you would have to work up the reaction to get it to isolate. Okay, so maybe a better answer in these conditions. Yeah, I think you have to use acid work up there. So we should probably add acid work up there, and just erase this, and just say H3O plus. Like that. Okay. All right. All right. Let's do letter C. Oh, man, you deleted it. Don't know why I did that. Okay. Say we have phosphorus and iodide. Okay, so this is the way to form PI3 to get iodine on here. But you know, so this is just a form of iodide. Okay. So what happens is you first form PI3, and then remember this converts this now to the this converts this to the this converts this to the iodide. Remember, like Pi SOCO2, and then also so we get this as our our structure of the first product. So yeah, let's see here. Huh, interesting. So I'm pretty sure we get this structure first. Let me just double check here. All right, 1 second here. Okay. All right. I see. Okay, so what happens is what we get as an intermediate is I'm pretty sure what happens is, so if you don't put a okay, so what happens is that first we're going to form this reactive intermediate. And then in the second step, what happens is sodium azide comes in right here. So the azide actually comes in and attacks this group here in an SN2-like fashion. And then we get our main product, which is the SN2 type chemistry we come to see, and which is this group right here. Okay. So, but yeah, I'm starting to wonder if there's a typo here. Anyway, actually, I'm just gonna think. Let's just think about this a little bit differently here. Sorry. I think for this problem, there's a typo. So what happens is the iodide will come here and attack this and get that off right. So it's an SN2 reaction. So you get some of this product. Okay, but then azide will come in and do an SN2 type chemistry here. So this will be SN2. And then for the first reaction, you just convert it to a good leaving group. So now it's a good leaving group. Okay? And then what happens here is now this should actually be wedged, I believe. Yeah, something like that. Okay, so we're kind of doing two SN2 type reactions. Yeah, so this alcohol should have, I think we should have made this dashed. It would make sense. Well, actually, let's just keep it wedged. Okay, so we can actually keep the same stereochemistry if we have it like that. There we go. Okay. All right. I think we'll call it good for that reaction. Now let's move on. So I don't know if this theory taught you about how to open rings, but you can open small rings with hydrogen, palladium, and carbon. However, you can't do that for cyclohexane. So there's no way to do that for cyclohexane. But for 2, we can actually do this type of chemistry. So reaction 1, no reaction. So this is no reaction. But for the second one, we can actually we can substitute the chlorine here. Okay? So the ring won't open. So this first step will only work on cyclobutanes and cyclopropanes. Okay? All right. Let's go on here. So H2SO4, 180 degrees. Oops. All right, so H2SO4, remember, it protonates this alcohol to form a carbocation. So we form this carbocation here when we lose minus H2O. So the mechanism is we protonate, lose H2O, and we get this carbocation, and then actually no, it's not that carbocation. So what happens is it's a methyl shift. So what happens here is, let me just draw it out here. Damn, my screen's glitching. So we protonate here to get OH2 plus, right? Then what happens is you have a methyl migration to form a tertiary carbocation. And then then the water, or the H2SO4 that's here. So now you have HSO4 minus. So anything that's relatively basic, it doesn't even have to be a strong base. We'll take this hydrogen here and do E1 type chemistry. So then our final answer is the alkene. There we go. All right, let's do some more reactions here. All right, so we can cover all our bases. So we have alcohol here. Now we're going to react it with 1 PCC. Okay, so this is just a solvent. So the second reagent is just a solvent. What's important is the first reagent. Then there's a second step where we have a Grignard reagent. So remember, Grignard reagents, they are a source of nucleophilic carbon. Okay, and then the last step is acid workup, where we work up the alcohol. So usually when you have a carbonyl, you're going to get you add a nucleophile to it, you're going to add a negative charge to the oxygen, so we need to protonate it. Okay, so the first step is we get the here, right? We form the aldehyde. Like that. Okay? So we formed the aldehyde, lots of hydrogen from both the oxygen and the carbon atom. Now, the next step is where this now will add. So this is a source of negative carbon. So this will now add to the carbonyl to give you this compound. So now we have O minus. And then what's attached here, here's the H that was originally there. What's attached is the CH2, and then here is the benzene ring. And what gets attached over here is the MgBr. Okay, and then acid workup, we're going to protonate this OH2 here, OH2 plus. So what happens is this bond here will break and get protonated here. And then what we're left with is pretty much yeah, so acid just makes it go faster. So what you get end up getting is this molecule right here. All right, so you get this molecule right here. And then the byproducts, what comes out of the reaction is some salt of magnesium bromide. And I still think you get like an extra proton out of it. So it's probably acidic conditions. Like that. Okay, so just think of the Grignard reaction as a good carbon nucleophile. It'll add to something electrophilic, and that's the C double bond O, breaking that bond, and now you can make an alcohol. So pretty cool. Okay. All right, now let's think of the bromide here, a bromide. All right, so there's going to be a lot of reactions here. Remember, it's E1 type conditions, so we're going to get a number of SN2 products. Oh, interesting. All right, so assuming no rearrangements, just think about we get the SN1 product here, then we get a bunch of alkenes for the E1 products. So you can think about it being a few different alkenes actually. I'm guessing. Well, it wouldn't matter, right? Yeah. Okay. So since this is a carbocation rearrangement, I'm not sure if Dr. Nassiri showed you all these carbocation rearrangements. But you can also get the alcohol here because of the hydride shift. So that's definitely possible as well. But you can also get a series of alkenes here. So yeah, so you can actually shift the so these are from carbocation. Oops. Come on. So slow. Come on. Sorry, this video is long, but guys, it's just for those who need it, okay? So these are from carbocation rearrangements. So if you rearrange to, well, I don't think this one's from carbocation rearrangement, but actually, I don't think any of them are. This one is from carbocation rearrangement. Okay, so kind of think about how that could work. All right, next here on the list we have an alcohol. So we also want to know what's in Jones' reagent because we might just write the reagents. We won't write Jones, and you'll still have to be able to figure it out. Okay. So this is Jones' reagent: chromium trioxide and sulfuric acid and water. They activate to form chromic acid, and then what happens is, remember, aldehydes goes to the carboxylic acid. So you're going to draw a double bond O and put the OH there. Okay. As for the mechanism, don't worry too much about that, but just know aldehydes go to carboxylic acids, secondary alcohols goes to ketones, and then tertiary alcohols don't react. Okay, next one here. I2. I'm not sure if you guys learned about this one, but you can oxidize. So iodine's a good oxidant. You can oxidize. So this is oxidation. You can oxidize 2 molecules of this. So let's just put 2 here. And then we get a disulfide bond. So this is how disulfide bonds and proteins are made, except you don't use iodine in the body, or the biology doesn't do that. Biology has an enzyme that kind of links these disulfide bridges. So say you have two strands of peptides to form the 3D protein structure. This is what it does. So it does this for the dipeptide bonds. And if you ever have, if you ever, get like a hairdo, perm your hair or anything, there's chemical compounds that actually cause the breakage and forming of these disulfide bonds. So your hair has proteins in it. So the how you get like a curly look or a wavy look in your hair, you're actually using some chemicals to actually break the protein backbone. Well, not backbone, but the interactions between two different strands of peptides, and that what causes these disulfide links to either break or form, and it causes your structure of your hair to look different and maintain its shape. So that's like a cool fact about what we can do in terms of these disulfide bonds. Okay, but anyway, let's move on here. We're in a long time. Okay. All right, so this will be the last reaction. I will go over a mechanism, go over some syntheses, and then lastly we'll do one spec problem for practice. Okay. All right, let's go. We're running late though because I'm supposed to be in my office. All right, so we have HI. All right, so what would happen here? So remember, when we have HI, it's a strong acid, so we're going to get some SN, some chemistry here. So we're going to form the protonate DOH. So let's just draw this here. So if we heat this long enough, this will leave. So this wants to leave as water, right? So whenever you have anything that can form water, it wants to leave. So now we get, so this formation is not very favorable because it's a secondary carbocation, but as soon as you quench the carbocation, the reaction goes forward. So what we have here is, so let's draw the H here so we can see it, and it's a planar carbocation. So now what happens is that this can actually do a hydride shift to get a carbocation rearrangement. So the hydrogen is very nearby. So remember when we have two groups that are nearby and they can react. They tend to react just like how epoxides form. So in this case, we get the much more stable tertiary carbocation. So now we have two H's here. Like that. And then what happens here is iodide is going to, so let me just draw this. And this bond breaks to the iodide. So now the iodide is in solution. Okay, so now the iodide is going to come in. So remember, iodide is not a very good base. So it's going to do primarily SN1 in this case. Okay, it's still a good nucleophile, right? It's a basic nucleophile, so we expect it to do primarily SN substitution. So we get, but this is an SN1, pretty much an SN1 type pathway. Okay. So usually when you have, you can form a somewhat stable carbocation, it'll probably prefer SN1. So now if this alcohol was primary, it probably still wouldn't do SN2, just because if a stable carbocation can form, that's most likely what's going to happen. So I would just think of that as the major pathway here. Okay, so that's the answer there. Now, let's think about what else to go over. All right. So, mechanism. So, you remember if we heat alcohols or ethers, there's a certain temperature where you will favor actually, um, you'll favor actually, you'll favor substitution or elimination. So we usually want that's higher temperatures for primary alcohols. It's towards like 180. That will favor elimination. But getting primary alcohols to react is always going to require some heat because you need to protonate the OH and get it to leave. So when we lower the temperature a bit to 130, we actually see a change in reactivity here, and we get primarily substitution. Okay, so let's draw the mechanism. So let's draw the mechanism. Okay. So what happens first is, so we're going to draw our alcohol here. Alright, so we should probably write this out a little bit here, where we have HSO4, and, you know, bonded to this molecule is an H. But, you know, let's just draw the whole structure out, just so we can see how it is done. Okay, so we draw an OH bond here. So we're going to break the HO bond. Now this is a reversible process, so should we draw reversible arrows? Then we get OH2 plus. So the question is this an E2 pathway or is this an S2 pathway? So it's kind of you shouldn't think like, oh, is this an SN2 or SN1? I thought only strong bases can do SN2 or strong nucleophiles. That's really that's where the kind of the complications come in. You can't really boil it down to that. We kind of just said that in chapter 6 and 7, or you know when we talk about alkyl halides, just to kind of differentiate the different nucleophiles for the reactions between alkyl halides. But in alcohols, you can have it can be anything really. So we kind of have to expand our horizons a little bit. Okay, we can't boil it down to that. But what you should think is primary with a Lehman group, SN2, secondary, tertiary, SN1. Okay. So we get this molecule here, and then another molecule of our alcohol. So not all the alcohols will be protonated because it's in equilibrium. So this alcohol now will come in and use its electrons to do an SN2 type reaction and substitute here, because now we have a great leaving group, water, one of the best leaving groups. And then we get substitution here where we get now an ether. Like that. And now the ether is protonated. And we have now our final product here, where now the we have I should write HSO4 over here. Because it was reduced as a byproduct. Okay. And then what happens now is we get water here as a byproduct. And then what happens is HSO4, or you could use water, it's okay, will come in. But this hydrogen is very acidic, so anything that's like can accept the hydrogen or act as a base will deprotonate it. Like that. Okay, and then we get to our final answer, which is the neutral ether product. All right, and then we reform the acid catalyst, H2SO4, or just acids regenerated in solution, and we get water. You can also write this as H3O plus. Okay. And then HSO4 minus. Okay, there we go. That's it for the mechanism. Okay. Now let's talk about synthesis. All right, let's do a few synthesis problems and then one IR. So this is all video. You know, just watch as much as you can or want, and then we'll go from there. Okay. So this is just kind of like a one day crash course into what you should know. So it should take more than a few hours, right? Okay. All right, synthesis. So for synthesis, we want to show how we would carry out these syntheses. So what we want to do is we're going to have a restriction here. So our restriction is use any reagent containing 4 or less carbons. Okay. So if you go work in industry, sometimes you're at a limit. You don't have the ability to just buy anything because maybe we're trying to find new ways to make these compounds without having to make some expensive intermediate. So we kind of have to think outside the box. So in this synthesis, we usually say what you should do is after each set of reagents, draw the product and then go to the final product. Okay? So let's look at synthesis A. Okay, so what's going on in synthesis A? We have this molecule. So sometimes we're given something, right? But sometimes we're not given the other part that we need. Man, I think my iPad's gonna die. Yeah, I just want a new one. Okay, so notice here in our products, we have something very complicated. So these are meant to be difficult because synthesis is not easy. Okay? So we have a methyl group here, but we also have a an OH group here. So we need to somehow think about how to form this compound. Okay. Oh wait, it's not OH. It's OCH3. I meant to write OCH3. Okay, so let's think about what we should do. Okay, so we need to add okay, so this one's a little bit tricky, and rightly so. So if you can do this one, you pretty much do it all the others. Okay. So we need to somehow flip this stereocenter. Okay, so we need to flip this stereocenter. So we need to flip let me see something. Okay. So we want to do this the easiest way possible, right? And if we think about our situation here, we need to get this alkyl group here. All right. So the only way to do that is to do a Grignard reaction, right? So we need to get this group into an. We need to get an alcohol and then form a oxidize it to a carbonyl at this position to add the ethyl group. So right now, what we're starting with, we don't have a lot of options, right? So what I recommend we do is we do something with this group here. Well, actually, we didn't flip the stereo center, so I don't think. I don't think we need to flip the stereo center. The stereo center is somehow staying the same, right? So, but we don't want to react the stereo center. We don't want to react the oxygen first to get the OCH3 because then we lose the ability to form something. To form the alcohol that we need to get to the ketone or aldehyde to add the ethyl group. So what we want to do is take this group here and kind of close it to form an epoxide. So we want to kind of do this kind of transformation first. Okay, so we want to do something like that first. So to do that, we need to use sodium to form an epoxide. All we need really is sodium hydroxide. Okay, so we're going to use sodium hydroxide, DMSO, because I don't think this thing will dissolve in water, so you can't use water. DMSO, okay, so what we get is now we're going to get the epoxide because it'll deprotonate and form an epoxide here. So we get this situation. Sorry guys, this might be slow because my iPad is responding really slowly here. Sorry about that. Okay. So now we need to get our OCH3 onto that carbon. So we need to open the epoxide on the more substituted side. So we're going to use methanol because that gives us the CH3O. And then an acid source like sulfuric acid. But we don't want to use a halogen. We don't want to use HCl because that will give us Cl minus, and that might compete with the methanol. So we want to use a non-nucleophilic acid, H2 um, H2 um, H2SO4 is our best option here. So what happens then is that the epoxide would open up and we get OH on this position, what we want, right? And then in one step, we can get the OCH3 on this position here. So it actually flips the stereo center. So remember, when we open up epoxides, it's still an SN2 process, even though we attack the more hindered side. So we're going to get a reversal of stereochemistry. So we somehow, in here, so to get the same stereochemistry, we have to flip the stereochemistry twice, okay? Flip stereo. Somehow, right? To get it, back to the same stereochemistry, you have to actually flip it twice, in this case. Right, so we can't actually flip it. So we could. There might be there's an alternative way of thinking about this. If we try to make the OCH3 first, it'll have some complications because then you'll have to get an alcohol on substitute the Cl for an alcohol, and water probably wouldn't be the best because they'll have some E1 products. So you get a wide mixture of products. So it's best to kind of use this epoxide method. But that's definitely an option. And if these questions were free response, you definitely get some points for that. But yeah, it's just a little bit complicated. So it's best to just do the I think even if you did try to do an SN1 to form an alcohol on the Cl, it might actually close from the alcohol on the right. But there's always other methods to think about, but usually this one is the highest yielding. Okay, so we want to make our molecule in the highest yield. Okay. So we want to make this in high yield. Okay. All right. All right. So now that we have our alcohol and our ether here, now let's think about what we should do. Okay, so last thing we need to get the ethyl group on there and the bromide. So first we should add the ethyl group, because if we just add the bromide, we're kind of stuck at square one. So let's use now PCC or Jones, or Jones. Or you could just write out all of the Jones reagents. CrO3, H2SO4, and then H2O. Well, maybe this file is so big that it's getting so slow. Okay. So what happens is we get the ketone now, right? And then we can now... So the only issue, we don't want to do SN1 at the start because you just get some E1 products. And then, yeah, it just gets complicated with the OH there. So you probably just want to either... Yeah, it just gets kind of complicated. It's because you have two potential good leaving groups there. Okay. Anyway, now we can add the ethyl group, right? We're going to use We need an ethyl group, so we're going to use ethyl magnesium bromide or ethyl lithium. And then use acidic workup to isolate now our new alcohol. Okay, and then what we get is we now get this group here. Okie dokie. So now what do we get? Heck, I don't know. Okay, let's see here. So we get okay. So what we get here now is hold on, let me just see if I can zoom in here. Flip the stereo center. How do we flip the stereo center? Huh, interesting. Yeah, I kind of don't know what the solution should be here because I'm not sure what actually happened in this reaction. Okay. So PBR and then oh, it's tertiary, right? So, huh. Okay. So I'm actually at a loss for words. So maybe yeah, I'm not sure. Like I look at the solution, I can't really get it. Okay, but anyway, if we were to flip it, pretty much flip stereo center. Yeah, I'm not sure actually. Will this be the BR? So yeah, you'll get this group, but it looks like I actually can't read it. Um, Yeah, it doesn't look. Okay, you know what? I think what should have happened, everyone. I think there's a typo, so it should have been this. Sorry. Yeah, because getting that flipped again makes no sense, and looking at this key I have here doesn't make sense either. So I think it's this. It should be flipped because there was a typo, I think, in the problem. Okay, so that doesn't change anything. So what we get now is OCH3 here, and then a methyl group right there. Okay, so I think we're good. Now the last thing to do, sorry about that hiccup. I mean, sometimes I'm doing this kind of on the fly, so sometimes things don't work as well. Okay, so we don't want, so the last thing is convert the alcohol to a bromide, but we don't want to use acid because it'll react with the ether. So we should use PBr3. And that's it. And we're done. There we go. So see these, so typical syntheses are more than 3 steps long. So I would prepare for that and just know all the reactions, do lots of practice. We can do some practice in my office hours on Tuesday, but please practice that. Okay, let's do one more synthesis and then one more, and then let's finish off with IR, okay? So the reason why in this case we didn't convert to the ether first is because you have to flip the stereochemistry. So I was right here. So flip the stereo. See, we have to flip the stereo here. So to do that, you need to use an epoxide. You can't just use acid and methanol. Okay? All right, let's do part B now. So see here, all our carbon reagents, they're all less than 4 carbons long. We are good. All right, B, we're going to take this cyclobutane and convert it to this much more complicated molecule, like so. Now, so to open cyclobutanes, we're going to use palladium on carbon. Okay, so we should open up the cyclobutane. So let's open up with hydrogen and palladium on carbon. Or just a palladium catalyst. So that's usually the catalyst that's usually used. Okay, so you see here we need to add a few groups here actually. So we need to, so we have 4 carbon atoms. So 1, 2, 3, 4. So we need to actually add this group and this group. And then the chloride at the end. Okay, and then we need a chloride too. So we should open up this ring first. So we get butane. So when you open up the ring, you get butane like this. Okay, and then okay. So now, let's see here. So there now in this step, there's a couple ways to do it. So you might have learned how to form an ester and then do hydrolysis or PCC, but we can do it in a number of ways actually. Okay. So to functionalize this, we should get a chlorine on here. So let's use Cl2, but you can also use bromine as well. I don't see why that would matter much. HB, and then we get the chlorine group on here. So that causes our radical to favor the secondary position. And so we get like that. And now we can do a few things actually. Okay. Um, yeah, let's see here. So can we do it directly a Grignard reagent? It might be a tad difficult. No, we can. 1, 2, 3, 4. Oh, we can. Okay. So what we can do here is, instead of using a lot of steps here, we can actually do a Grignard reagent. So we can do 1 magnesium ether. So form a Grignard reagent. So you can put the solvent here, ether. It's usually ether or tetrahydrofuran, THF. Okay. So what happens here is we form the Grignard reagent here. So we get this molecule in solution. Okay. And now you see here that it represents pretty much this part of the molecule. Okay. So now we have this fragment here. Okay. So that's good. So now we can add, now if we count the number of carbon atoms that remains, 1, 2, 3, 4. So that's within our limit. So we can make this a carbonyl group and do a Grignard addition. So we can do H. So 1, 2, 3, 4. 1, 2, 3, 4. Like that. Oh, but that actually poses an issue, doesn't it? Because the alcohol will be on the wrong carbon atom. So we actually can't do that. So if we did that, right, the alcohol would be right here. But we want it at the center where the chloride is, so we can just substitute it. So let's not do this method. So, it won't work. Okay? So see, there's always a method here. Alright, so we can't actually do this step, so let's backtrack. So the only thing we can do now is we need to get the alcohol. So we need this OH here, the Cl. We need to get the alcohol forming on that carbon. So the only way to do that is to convert this chloride into an alcohol. So we don't want to use SN1 type chemistry because you get a competition with E1. So what we want to do is do this. So we're going to react it with sodium acetate. So sodium, this will be negative, this will be positive. So we have an active nucleophile. Do SN2 type chemistry first. And then we're going to treat it with sodium hydroxide and water. And this will cleave the ester to give us our alcohol. So you'll learn about this mechanism, but I could just show you. So what happens first is you get this. Okay, so this is what happens first. And then sodium hydroxide is a source of hydroxide. And what actually happens is, it's a little bit complicated, but you can essentially think of it like it's doing this. It's tagging a double bond. And then, so I'll just draw it very quickly up here. SOH, like so. And what happens is this will kick back down and kick this off as a leaving group. So then what you get is O minus, like that. And then you get acetic acid. And we know acetic acid is very acidic, so this actually picks up the hydrogen and this bond breaks over there to give you your alcohol. And then as a byproduct, you get sodium acetate again. So yeah, you actually get acetate back out. So this is the major product though. And then you also get plus. If we drew the arrow here, you get sodium, you get acetate now. Like that, okay? All right, let's keep going on here. Oops. Delete. What the? Delete. Okie dokes. Alright, so next thing we need to do is oxidize this to the ketone because we need to add this group here. So the only way to do that is through Grignard reaction. So we need to oxidize this. So we can use PCCCH2Cl2 or Jones or CrO3 / 2SO4 / H2O. Okay, so we now oxidize this to the ketone here. And now we need to add the carbon group. So we're going to add the 4 carbon group I kind of drew above there. So that's going to be, let's use a Grignard reagent or an organolithium. 1, 2, 3, 4. 1, 2, 3, 4. Magnesium bromide. Or the same kind of lithium-based reagent. 2, and then H3O+. All right, so what we get here is now we're getting the alcohol, and then this carbon group is going to form 1, 2, 3, 4, and then the methyl group is going to, the ethyl group will be right here, and the methyl group will stick down there. So we kind of added it here, so we can actually color code it here. So here's the blue. Here's the methyl group. And then here's the alkyl group we just added. Okay? And last but not least, we need to... Oh, that's weird. Last but not least, we need to convert... Lastly, we need to convert to the chloride, and to do that, we can use SOCl2 or PCl5. And usually we add a base, like triethylamine. To neutralize the HCl that's usually generated in this reaction. So that's the best way to convert it to the final product there. All right, that's it. So that was long. Man, I didn't know this time was getting out of hand. So it's almost 4 hours. Jeez, okay. Well, there's a lot of material, right? So I want to make sure everyone got their bases covered. Okay, so if this doesn't make sense, review more synthesis problems, know your reactions. You can always kind of think of these as sort of patterns to recognize. But if there's any questions, reach out. But please try more practice based on what I've talked about in this section. Okay? All right. Last but not least, spectroscopy. So you can expect at least one spectroscopy question where you have to solve the structure. So let's go over how we should do that. It'd be more helpful if this thing didn't lag every time I drew a letter. Apple, you gotta step up your game. Spectroscopy. I always kind of forget how to spell it. Spectroscopy, like scope. All right, our compound is C10H20O2. All right, so first, let's determine the degrees of saturation. We're going to include the degrees of saturation for partial credit. If we were doing a kind of free response, but most likely now, expect kind of like either free response. Well, I wouldn't say that, but in your future classes, most likely it'll be free response. But in our class, it's going to probably be multiple choice, so you'll have some answer options. So use your detective skills and your to eliminate the choices it cannot be, and to arrive at your final answer. So I did make a key for the last spectroscopy quiz on. It's on Canvas, so if students are interested, please go take a look at that and see how you can kind of tackle these spectroscopy problems when it's multiple choice. It doesn't have to be you get it or you don't, you panic and you don't. There's some tips and some strategies to use for any kind of multiple choice exam. Okay, so spectroscopy. So let's calculate degrees of saturation. So remember, it's 2 times C plus 2 minus the number of hydrogens. So let's do, and then plus the number of nitrogens and minus any halogens, not oxygens. So X equals halogen, okay? And then we're going to divide this all over 2. So I'll do 2 times 10 plus 2 minus 20 divided by 2. So that's going to give us a degree of saturation of 1. Okay. So what does this mean? We can have, so 1 double bond or 1 ring. So if we think about our structure here, if we look at the, let's draw the NMR spectrum. So here's 5. So it's going to be hand drawn here, but I assure you that the peaks can be readable. Okay, so this is 1H, and it looks like it's 7 peaks if we count all the apexes there. And then we have something that looks like a triplet here at 2H. Then at 3, so here's my ppm. Okay. So at 2 ppm, and then we have 1 over here. All right, at 2 we have, looks like a quartet, and then here's a triplet. So oftentimes we will not give you the integration. You have to be able to read it, because in real life you're not allowed to do. You have to interpret yourself. And then at 1.5 here we have a 1, 2, 3, 4, 5. And then here we have 1, 2, 3, 4, 5. So 2 peaks that integrate to 5 there. I mean, have a 5 peak if we count them. So I would just label the peaks what they are, so you have a better indication what to expect there. So you can so you know what the peak is, so you don't have to go back over it again. All right. Hopefully it doesn't crash because I don't want to draw this again. Okay. So let's use 1 here. So here we have a triplet for 3H. And then right here we have a big doublet. Okay, this is for 6H. All right. So we count our hydrogens, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, plus 9. That gives us 20. So it can't be a ring, right? Well, it could still be a ring, but you just have a methyl group sticking out to the end. But I doubt it. Usually, it's not a ring unless you see some. Usually, it's hard to rationalize if it's a ring unless there's like symmetry involved. But usually we don't. It's not usually a ring. But first, let's look at the IR. Okay, so the IR is right here. So here's the NMR. Now we have IR here. So the IR looks something like this. Actually, I can't even draw. Okay, so this is 500. Remember, I told everyone don't look at anything past the 1500 mark. It usually won't help you. Okay, and here's 1500. All right, 2000 here. And then this is a little past 3000. And then this is 4,000. So here we have wave numbers. And here is percent. Percent transmittance on the side there. Okay, so what could these peaks be? Well, the only observable peak, I think, is this one, and it's a C double bond O. So we know that it can't be a ring, it has to be C double bond O, because that's around 1700. So we have 1 degree of unsaturation, and it has to be saturation, and that has to be a double bond O. Okay? So now, if there wasn't a double bond O, you would kind of assume that there's nothing else in there, and it would be a ring. But in this case, it's not a ring. Okay. So let's interpret the spectra. All right. So at 4, we have 1H next to a lot of... So let's look at here. So the easiest peaks to decipher, in my opinion, are these peaks downfield. So it's at 4 ppm. So remember, at 4 ppm, that usually means your hydrogens are near a carbon atom, or attached directly to an oxygen atom or electronegative element. In this case, the only electronegative element we have is oxygen. So we should kind of think about this being attached to oxygen somehow. And since there's 2 peaks, that means there's 2 groups of hydrogens attached to the oxygen. So I think this is an ether for the other oxygen. Okay, so maybe we have something like that. So here, and then there's going to be a multiple for 1H, and then there's a 2H for a triplet. Okay, so maybe one side is connected to another CH2, which is connected to the rest of the molecule. So this will explain this peak. Okay, it's downfield, and it's next to a triplet. Now this 1H looks like it's a multiplet, and we counted 1, 2, 3, 4, 5, 6, 7 peaks. So it looks like a multiplet. So this must mean it's attached to 6 neighbors, and that could only be 2 methyl groups. So this H represents this hydrogen right here, and that's because it's downfield as well. So we have now attached these 2 groups, and these 2 methyl groups must be due to this methyl 6H peak right here. So we could just label them right here. A. So this is hydrogen A, B, B. And now we have a bunch of hydrogens on C. Well, actually, I won't draw them out. I'll just say these are the methyl groups, okay? C and C. C, C. So this gives us peak C right there. Okay, now we have to figure out all the rest of these groups here. So we need a quartet, triplet, and a series of pentets, and then a triplet. So, if we think about it, a pentet has to be two CH2 group connected to 2 other CH2 groups. So something like this. So a pentet would look something like this, right? R, CH2, 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 R. Okay, so if we look at these two hydrogens here, right? They would see 4 neighbors each. So there's if there was 2 hydrogens here, 2 hydrogens here, and 2 hydrogens here. So these ones. So these hydrogens would see pentets, right? Because they have 4. If we look at one hydrogen, right, like this one, it'll have 1, 2, 3, 4 neighbors. So it should look like pentets. So these could actually be these peaks right here. So let's label those as D and E. So this would be peak D, peak E. It's kind of hard to determine which one is which, but I don't think it matters too much. Okay, and then we have a 3H at 1 ppm. That's usually, we could say this is usually a methyl group somewhere. So let's try to figure out where that would be. And then the last 2 peaks are at 2H and 2H. Okay, so remember, peaks that are around this region, too, are usually bonded to a carbonyl group or a double bonded O. Okay, so they're usually these types of hydrogens. And say this is an R group, right? And this is an R group. Okay, so it makes sense that these 2 are connected to the carbonyl somehow. Okay. So we're going to draw the carbonyl and say, okay, they should be directly connected to the carbonyl because they're around 2 ppm. So 2 to 2.5 is usually, or 1.5 to 2.5 is usually you're attached to some carbonyl. So let's just label these as E, C, D, E. Let's label this the methyl as F, and this is G, and this is H. So these would be G and H. Okay, so don't worry too much about. Well, actually, we can actually think about this. Okay, so we figured out those 2 pentets at 1.5. That CH3 is probably a triplet. It looks like a triplet, so it must be attached to a CH2. So, and one of these CH2s looks like a quartet, so maybe one of these CH2s is bound to the methyl group, like this. Okay, so that will explain peak H and the CH3 there. So now we have to figure out how to combine the rest of the molecule. All right, let's look at peak B. So peak B, right here. is a triplet. So it must be next to a CH2. So, and then peak G, however, is a quartet. Oh wait, sorry. No. Let me see something. I think I mislabeled these. So we should label this one as G, right? Because now this is the quartet. That makes sense. Now the other one is at a triplet. So this H peak should be a triplet. So it should be next to the CH2. So we can actually combine the next fragment. Let's label these fragments. 1, 2, and 3. So how should we label these? Okay. So we can't directly connect. So we can think of this as the CH2 group, right? So maybe we can connect that to this part of the molecule. However, then we can't really connect this group here, this whole fragment here. So we should probably connect this fragment first because it doesn't have one end that's capped. So it can actually serve as the middle part of the molecule. So let's connect parts 2 and 3. So first, let's connect parts 2 and 3. So now we have, let's do 2 and 3 here. So now we have, okay. And then here's the CH2. We're going to combine it to a series of 4 CH2s now. 1, 2, 3, 4. Okay, let's see how we're doing. Let's move this. Maybe let's move this a little bit somewhere else. Do I have room? Okay. There we go. All right, so now we have the 4 CH2s, right? So we have, let me just highlight them in blue, the series of CH2s that we wanted to add. 1, 2, 3, 4. And now we can add the last part of the molecule, which is now going to be the CH2, 1, 2, 3, 4, the CH2. The CH2 connected to the oxygen. So it'll be this, and then we connect the rest of the molecule here. So that's a purple group, and there we go. So let's count our atoms. So we have a structure. Is it right? So let's count our atoms here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, actually, no, we're too many carbons long. So maybe we did mess up somewhere. It is C10, right? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Huh. Ah, okay. Oh, we did add too many. So remember this this CH2 here, and it represents this CH2, and then this CH2 right here represents this CH2 right here. So we can actually, this is one of the reds, the one of the CH2s we already drawn. So we can actually omit that. Okay? So now let's connect it a little bit better here. So we're going to CH2, then add 2 more CH2s. 1, 2. And here's the CH2. Now it's going to attach to the oxygen. So yeah, it's tricky sometimes. So we have to kind of be careful where our peaks are and try to piece them together as best as we can. All right, now let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So still a little bit off. Okay. So we should just add, so since we started with this fragment here, see right here. Okay, so let's just add 2 CH2s because right now we have 3 of the peaks, the CH3 and the two CH2s at 2. So now let's add the 2 CH2s from the 1.5, 1, 2, and then the CH2 from the downfield peak there, and then we're going to attach the oxygen, and now this should be correct here. 3, 4, 5, 6, 7, 8, 9, 10. There we go. So just be careful that you don't overlap CH2s, so it can be kind of confusing. So, but it's probably best to kind of write the fragments and then connect the pieces. And then as you're connecting the pieces, cross out the peaks so you don't overcount. Okay? So this is actually the structure we are looking for. And it makes sense, right? Because if we label these peaks now, these should look like a doublet. This should look like a, this H right here should look like a multiplet right there. Okay, this one's a triplet downfield. This one would be a pentet that we see at 1.5 for 2 H's. And then we see a triplet at 2 ppm next to the carbonyl, and then a quartet at the 2 ppm, and then a triplet here for the methyl group 3H, and it matches our peaks in our spectrum. So that is our structure. Okay. Right, so those pieces, they do look complicated, okay, but if we think about the structures, we can actually piece it together quite nicely. So what I recommend is always try to see what pieces work. So I can write a few pieces here, but I think it's I think we did that exactly here. So we did kind of think it like this, and then the key pieces was the carbonyl with the CH2 connected to CH2, CH3, and then we figure out the series of CH2s that we need. So that is the answer. Okay, guys, so that was long. It's already 4 hours. I will edit this and post this. But good luck. I know it's tough given the changes we had during the quarter, but I know you can do it. Study hard, work hard. Don't stop until you're sick of hearing this stuff, and then on exam day, do your best. All right, I'll see everyone next time.